Okay, thank you so much for the invitation, all three of you. I'm going to make this a little shorter than I was planning because of the delay. The problem with technology is that sometimes it's not always so perfect. So this is, I want to emphasize this is joint work with Huy Nguyen, who's at Brown right now. And I'm going to talk about Stokes wave. So, whoops. There we go. Okay, sorry. Okay, I'm going to skip that. Okay, what is a Stokes wave? It's a periodic traveling water wave propagating in one direction. So we ask whether it's stable or unstable. And go to the bottom of this slide. If you make a perturbation, a small perturbation initially of the wave number, then modulation instability means that you really get instability, that the waves really deviate from the original Stokes wave. This is sometimes called the Benjamin Fear instability. Why is this? Okay. Oh, okay. So here's a little picture of nice, simple 2D traveling waves at the bottom of this picture. And that's the kind of wave I'm talking about. Small ones, actually, it's not so exciting in a way, but the instability is the big thing. So the assumptions are written at the top of this slide. We take the Euler equation. I'm going to write them down very soon. There's a free boundary between the water and the air. And then the two boundary conditions, well, no, the water itself is incompressible, inviscid, irrotational, and I'm assuming it's two-dimensional, like in this picture below. And the pressure, and then the two boundary conditions. One is that the pressure on the surface equals the air pressure, and the other one is that particles on S remain on S. So I'm going to write this down precisely in a moment. So here's a little sketch of just a sketch of the 2D water wave. The surface is given by a function eta, and you have a flat bottom, and it's periodic. The Stokes, a periodic wave, so a period here is L. Okay. And here it is precisely the model I'm talking about. Okay, this is, so we have a fluid domain omega. So just, it's this system written in red. So phi is the velocity potential. It's harmonic under the assumptions of incompressibility and irrotationality. And then on the bottom, the bottom, I'm assuming now the bottom is infinite in this lecture. And so the velocity goes to zero way down at the bottom. And then you have the two boundary conditions. The first one here says that the pressure is constant on the surface. And the second one says that the particles which are on the surface remain on the surface. So I'm going a little faster than I might otherwise. Okay, so, okay. So the most important, okay, so this instability was sort of discovered with, which was heuristically discovered by Benjamin and Fear, and also by Whitham and Lighthill back in the 1960s. And there hasn't really been, there's only been one proof, and that is by a very important paper by Bridges and Mielke in 1995, who proved it in the case of finite depth using a center manifold type of proof, spatial dynamics. And my talk is about a completely different proof, well, not completely, but largely different proof that works for either finite or infinite depth. So there are many papers about approximate models of waterways. There are many, many famous approximate models, NLS, KDV, Whittam equation, and many others. And this same question that I'm talking about has been discussed by a whole series of people in the last 15 years, which I list here, Bronsky and so on. And even the nonlinear instability has been proven for some of these models by Jin, Liao, and Lin recently. But we're talking here about the full waterway problem without these kinds of approximations. And in our result states, the main result is that you have linearized instability. And so the proof of Bridges and Mielke is not applicable to the infinite depth case, but we give a proof that works for both, as I mentioned before. And our method of linearization, we keep the physical variables, and so it makes sense for the nonlinear problem, and we think it will lead to a proof of true nonlinear instability. But I will focus only on the linear instability in the case of infinite depth. So here I'm trying to state the result a little bit with some care. If you have a Stokes wave, say of period 2 pi, and its amplitude is epsilon, small, and then you take a perturbation of the wave number, mu, which I call mu, and this means that you take your 2 pi periodic functions and multiply by e to the I mu x, and mu is also small, and L is the linearization. It's an operator, and the theorem says that L has an eigenvalue lambda with a positive real part. And in fact, the eigenvalue, which tells you the growth, like e to the lambda t, the lambda is given in red here. And you see it has an imaginary part, but it also has a real part, 1 over 2 square root of 2 times mu epsilon. And that's the thing that gives you the instability. That's the result I'm talking about. And there is numerics. There are various numerics, but the most precise and specific related to this problem that I know about is by DeConnick and Oliveras, which shows you the curve lambda as a function of mu. And this curve is totally consistent with our theoretical result. Okay. So the most important thing here is to formulate the water wave, at least by our method. We formulate the water wave equations in an appropriate way, in a useful way. So the first set of equations 3 is what I just copied from before. And now you consider the Zakharov method, which is to just restrict the velocity potential to the surface. And then eta is the function which gives you the surface. And then 3 becomes 4. The 4 equations in 3 become the 2 equations in 4. And they involve the Dirichlet-Neumann operator. This is the Zakharov-Craig-Sulem formulation. Dirichlet-Neumann operator takes you from Dirichlet conditions on the surface to Neumann conditions, as indicated at the bottom of the slide. So we're going to be working with equations 4. These are nonlinear equations. Okay, so I'll take the period to be 2 pi, I'll take g, gravity be 1, and now the Stokes wave. So way back 100 years ago, Nekrasov and also Levi-Civita proved that you have a curve of nice traveling waves for small amplitude by showing that the power series in epsilon converges. And Stokes, many years before that in the 19th century, actually had an expansion for what the wave should look like. That's equations 5, which we will use. And now we want to linearize. We have to linearize this system in red. So we have to use, the way we do it, we have to take the derivative, the Frechet derivative of G of eta psi. Now I'm going to use star, an asterisk, to indicate the Stokes wave of amplitude epsilon. So epsilon is small, you have the little Stokes wave, and then you have the shape derivative formula, which tells you what the Frechet derivative is. And we also use the so-called good unknown that Alignac suggested. And then the system that I showed previously becomes 6 and 7 at the bottom of the page. So we're going to be working with 6 and 7. And they act on some periodic functions. Now we have further, a very important thing is because the domain is unknown, the surface is unknown, so the domain omega is unknown. And we flatten the free surface in a standard way by conformal mapping. So here's a conformal mapping. And in terms of the conformal mapping, I'm going to skip the details of this slide. The previous system written in red becomes this system written in red. It doesn't look so formidable. I've made some change of variables, a fairly mild change of variables. And I flattened the boundary, but the boundary is fairly flat. It's a small amplitude, fairly flat anyway. So flattening the boundary by conformal mapping. And then it looks like this. And there are two variable coefficients that appear in 3 places, P star and M star, which depend upon the Stokes wave explicitly. That's in the slide, partly in the slides that I skipped very quickly. And they depend upon the Riemann stretch, which means the conformal mapping. And if you look at small epsilon and expand and use Stokes expansion and some other expansion, then these two coefficients are written at the bottom of the page in terms of epsilon. So that's our system, and then we're going to look for instabilities. So here we look for instabilities. So we do 2 things at the top of the page. Mu, we have mu, a small parameter, which changes the period. So uj, so there are two components in the system, W1, W2, and we're changing the W1, W2 into U1, U2. The U's have period 2 pi. E to the I mu x, U of x, to have a different period, a period capital L. And then we look, and we want to look for growth in time. So we have e to the lambda t, and the whole purpose of this lecture is to show that there is a lambda where the real part of lambda is positive. So you get growth. And it's convenient to take the Floquet parameter mu to be a rational number, because then Wj has period L. So we can do that, but we can, in some sense, we can also avoid that. But let's just say mu is a rational number for the time being. And then the system, which is here 8 and 9, takes the following form. See, the time has now disappeared because it's e to the lambda t. So here's the lambda on the left side of the equation. And then in red here is the linearized operator. This is the operator we're working with. And so we're going to be working with this operator. And okay, so here now with this operator defined, here's a more precise statement of the theorem, of our theorem. It says that if epsilon is small and mu is small relative to epsilon, then the operator does have an eigenvalue with a positive real part. And I've repeated the expansion. The hard thing is to find show there is such an eigenvalue with positive real part. And so notice that if I take epsilon equals 0, if you take epsilon, here's a matrix L mu epsilon. If you take epsilon equals 0, then this simplifies and takes this form. When epsilon equals 0, which is okay. And then it takes this form, and you can see that you can Fourier transform, there's no variable coefficient. And you see, what we see is that when mu and epsilon are 0, then you have 0 as an eigenvalue, and in fact, it has multiplicity 4, exactly 4. And when mu is not 0, then you have 4 imaginary eigenvalues, which I indicated in these formulas. Very simple. So the 4-dimensional, the eigenvalue at the origin, which is 4-dimensional, splits into 4 different imaginary eigenvalues. And now we take mu equals 0, but epsilon not 0. And when epsilon not 0, we still have 0 as a multiplicity 4 operator. And you have 4, we use explicitly the 4 eigenvectors in the null space. And they satisfy, well, the first 2 are actually in the null space. The other 2 are generalized. They satisfy equations 13. That is, L of U3 and L U4 aren't 0, but they're equal to multiples of the other guys. And we also normalize. That turns out to be important. And then we have U1, U2, U3, U4, which are those eigenvectors. And those eigenvectors have these expansions, which we explicitly use later on. Now, how shall I, how much time do I have? Monica or?
About Walter, you can talk till 5 o'clock, so you have 20 minutes.
Oh, good. Okay. Well, that's great. Okay.
So please take your time.
Okay, I appreciate it. Okay.
Okay.
Good. Otherwise, I would only have 5 minutes. Okay.
Okay.
Right. So, okay. So here we have these eigenvectors. That's when mu equals 0. Those are eigenvectors at the origin, lambda equals 0. Okay, now we want to take those and perturb in mu. So we fix the epsilon and we perturb in the mu. And we use the Lyapunov-Schmidt method, which the idea is to reduce the whole problem into a 4-dimensional problem. And so this is the standard Lyapunov-Schmidt splitting. We take the projection. So script u, which I have here near the top of the page, script u is the generalized kernel. It's the 4-dimensional space. And script u perp is infinite dimensional space. And now, and we just write the equation, which is L minus lambda identity equals 0 into 2 parts. And okay, so the first one is the, 18 is the infinite dimensional part and 19 is the 4-dimensional part. So what one does in Lyapunov-Schmidt is one writes down a solution U of the system as a linear combination of the UJs, the four-dimensional guys, plus an infinite dimensional remainder W. And then W, then by linearity, W is a linear combination. And therefore WJ, what I'm calling WJ, J equals 1 through 4, WJ satisfies 20. So that's, okay. So then, now I just recall for you in red, that's the linear operator we're talking about. And we decompose L into two parts. Notice that mu appears linearly in every place except the upper right corner where there's an absolute value. So you have to be a little careful about that absolute value, but it's almost linear. And LU epsilon has the form of a fixed operator plus mu times another fixed operator. And there's no mu squared term. And then, okay, whoops, I have question marks there. Okay. Anyway, so we write the four-dimensional system, and so then, okay, so the four-dimensional equation now takes, we have to solve for the WJ. That's the infinite dimensional part, and we have to invert. So pi is the projection onto the infinite dimensional part. And pi L0 epsilon, we have to invert that to find a formula for WJ. Okay, so we do that. And we call the inverse Xi epsilon, which I wrote in red here. And that inverse it's a good inverse. And we can write down the solution. Now the previous equation at the bottom of this slide, you have the thing we're going to invert in the first term, and the second term on the left side, it has a mu and a lambda, but mu is going to be small and lambda is going to be small. So therefore we can once we invert pi L, then we can invert the whole thing because you got small perturbation. And so we've just written the Neumann series. And those are the WJs. Okay, it looks horrible. Okay, so now we insert those WJs into the formula. So here near the top of the page is the four-dimensional system written in terms of unknown constants alpha 1 to alpha 4. And therefore, WJ, of course, is given rather complicated formula, but but we just want to find a non-trivial solution of the alphas, and that means we just want the determinant of the matrix that you can see here to be we want the determinant to be 0 to make sure there's a non-trivial solution. So that's the determinant of a 4x4 matrix, which I write in two different parts. I write as A, there's a minus lambda identity, and then there's a B. And the A and the B are given, you see the A, if we ignore the so-called sideband functions W, then the A matrix, 4x4 matrix, is just basically LUJUK, normalized. And the B is LWUK, which you usually ignore. We call that the sideband matrix. And I epsilon is almost the identity. I'll skip the details there. So we want to solve this equation determinant equals 0 for lambda. So I call that determinant, I call that script P. And so what we want, we're going to get the instability if there is a small number mu such that this fourth degree polynomial has a root lambda small with a positive real part. That's all we're trying to do. And now we expand. We expand everything out. We have small parameters, epsilon and mu, and also lambda will be small. It'll have positive real part, but it'll be small. And so here, so then we do some long, very explicit, but quite long calculations. There are many terms. This is a 4x4 matrix. So you have 16 entries. Anyway, we compute and we find that the part, if we ignore the B matrix, which is the sideband matrix, then we get this expansion for the determinant. Now we want to find a solution lambda with a positive real part. But you see in blue here in formula 27, we have, it looks like lambda is approximately 1/2 I mu. That's imaginary, no good. That's not what we're looking for. So we have to look at the other term, that other part involving the B, which I write in red to emphasize it. And here's the result of similar calculations. When you look at the part involving the B in a formula 28, then you get a term which is -1/8 mu cubed epsilon squared. Now it's not so clear which how to do the approximation, which powers of mu and epsilon we have to keep are the major terms and which ones are error terms. But we've written very carefully the error terms. So we have some error terms in the second line of 28, and then we have more error terms in the third line. Notice in the third line, you have epsilon cubed, which turns out we can basically ignore. And then we have mu to the fourth and lambda to the fourth, which we're going to basically ignore. But the other terms in the second line have this combination 1/2 I mu minus lambda in them. Anyway, when I combine these calculations, the last two things, you get equation 29. 29 says you get the first term in blue and the second term in red. And that second term in red will give us the instability. Okay. So, okay, so now we look at here I've written again okay, so here's in the box I have the thing we want to find the root lambda of this guy. And notice that in all the main terms on the right hand side, mu appears cubed or lambda appears cubed, or it's a combination. In the pair mu lambda, it's cubed. So we rescale. A little rescaling, we write lambda at the top of this in red. Lambda equals mu times another variable we call gamma. And then we can take the mu cubed as a common factor of all but the last terms. And so the main terms are on the first line of equation 30. And you see, and I've written you still have the 1/2 I minus gamma squared. We want, gamma is the thing we want to have a real part, non-trivial real part. And then you have the -1/8 epsilon squared, and then you have these other terms. And so if you just look at the leading, so if we just look at the leading, we're going to look at the leading term. If you look at the very leading term, just the blue and the red part, you're going to see you're going to have gamma equals an imaginary thing plus the square root of epsilon squared over 8, which is what we want. And then we have the other terms. So call the main terms, we call the main terms Q tilde, main terms in 30. And Q tilde actually, so even with these other terms which are written in black in 30, you still have a root which is I divided by 2 plus epsilon 1 over the square root of 8, and then some higher order term of actually higher order powers of epsilon. That's exactly what we want, and then we just have to use a little simple implicit function theorem and say that same basic thing happens for the whole polynomial. So yeah, so you're going to have these two roots. One has a positive real part and one has a negative real part. And the final theorem says, here's the final theorem 32. The theorem says you take epsilon small enough, and then you take mu, it depends on epsilon, and then the polynomial has at least 2 simple roots, and here they are. Equation 32 has this form where the G's are smooth functions. So for mu and epsilon small, those 2 last terms in 32 are negligible. And that's the proof. And so I hope this has been understandable. A little bit rushed, sorry, but there should be a few minutes for questions. Thank you.